So thanks so much for joining, everyone. Thanks for hosting, Amir and Miriam. Really excited to share this talk and do some Q&A with you all on self-improving large language models. I think probably today is about practical LLM usage. This may be one of the less practical talks. We'll see, but if you stick with it, I promise that there's some really interesting research that we're going to dive in here. And hopefully, even if it's not practical for you today or tomorrow, it can be something that can help spark some ideas for you going forward. And I think you'll enjoy it. So just briefly about me, I'm Gordon. I'm based in Toronto, and I've been working at a company called Ada for about 6+ years. I've been working on the machine learning team. Ada is a company that helps automate customer service interactions. And yeah, I've been working on natural language processing there for quite a while. So as I was preparing for this talk, Amir will remember the days when we gave talks in person. I kind of realized that in 2019, I gave another talk about a paper in a fairly similar topic. And I'd totally forgotten about that until I was getting into this. And so I was asking myself, why do I keep talking about this topic? Like, why do I keep coming back to it? In this case, it was a paper from Google and Carnegie Mellon on unsupervised data augmentation. So strategies to generate new training samples from unlabeled data. And yeah, so this was pre GPT-3 and all of this. So I think one of the reasons that I keep coming back to this topic is I think it's really, really cool. The idea of using unlabeled data to improve models is fascinating to me, and I think the research is only getting more interesting in this space. And again, I think you're going to find some of these papers quite interesting too. But also beyond that, I think there's several reasons that this area is important. First of all, as we know, large language models themselves are trained on vast amounts of unlabeled data, and they're doing this in a self-supervised manner where they're taking say a bunch of text from the internet and converting it into a task of predicting the next word. And so large language models continue to be showing a lot of impressive results as we scale them on larger models and more data. But I think another thing that's emerging and is becoming more of a trend is that, or reality, that these language models, as they're getting better, they're able to produce higher quality, more human-like text, we can say, and therefore the training data that you can generate from a large language model is getting better. And so it's becoming more and more feasible to use large language models themselves as part of the process of creating new data for training. And so yeah, I think we can. What we'll talk about today are techniques of using unlabeled data to further improve large language models. But these are techniques going beyond just the next word prediction task that is so central to LLMs. So these are some interesting new techniques, and so hopefully, I think over the future, sort of predicting that we'll see these methods become more and more prevalent, and there'll be more of them that'll come out. And I think also there's opportunity to think about these techniques and approaches in terms of your product space or the area you're interested in, and how you can potentially create valuable data sets and improve your language models. So one thing, we're going to talk a lot about using LLMs to kind of replace the process of using humans for annotating training data. But I want to call out at the beginning that, um, in my opinion, this trend is not a suggestion that a human data annotation is going to become less important over time as large language models get better and better. I think likely the rate of human data annotation in the world is only going to grow. I think we're going to have more data annotation, more people doing data annotation as a job over time. So I see that field growing, but I also see the field of LLMs generating training data growing. So in my opinion, I would look at it that the amount of data that we're going to need to annotate now and in the future is simply going to be beyond the capacity for humans to annotate all of it. And so I think the trend that I'm expecting to see is that humans will become human annotations will be used more for creating ground truth evaluation data sets to really get super good at evaluating the models that are being created, and that the generation of training data, annotating training data, is going to move more and more towards LLMs. So that's kind of my take on this. And let's get into the topic of self-improvement. There's a few different terms and techniques that are discussed through all these different papers that I'm going to share. I don't want us to get too bogged down in definitions, but thought I'd provide some initial ones here. So self-supervision, we already mentioned this. This is the approach of a model constructing labels from an unlabeled data set. So again, the example of a language model that is taking a Wikipedia page that can be considered unlabeled data and converting it into a labeled data set by hiding words in a sequence and trying to predict each word as it goes. So self-supervision. Data augmentation is more or less generating variations of an input training data, usually through transforming it in some way. And then self-training is a process that requires some initial labeled data that's used in training a model, and then the model typically in some form will make predictions on unlabeled data and further train itself on those predictions. So again, we're not going to track these too closely throughout the presentation. I think they're all discussed at different times in the papers. What we're not going to cover today, but an area that is really interesting, is using LLMs for generating training data for other models. And I think that actually might be one of the more practical ways to use LLMs for your purposes. Is, let's say you want to do something like a name density recognition task, but you need to be doing it at really high volume, and it's not cost effective or latency effective to use ChatGPT API. And so what you can do is use an API like OpenAI's to generate a bunch of sort of labels. You can give it the task of name density recognition, give it some input samples, or ask it to create some, and then use those labels in training a downstream model of your own that is maybe faster to run and you have a bit more control over. So we're not going to get into that too much today. The papers don't talk about that, but that is an active area of research, and lots of people are exploring that. So suggest you consider looking into it if you haven't already. Another thing I realized as I was preparing this talk is that we're going to mostly talk about four or five different papers. And for each one, they're, again, talking about this idea of automatically generating or labeling data sets. And I realized that each one sort of has an equivalent paper or papers that that are doing the same thing, but with human annotated data. So just wanted to highlight those. We're going to talk about the Toolformer paper that's teaching models to use tools, language models to use tools. And the Lambda paper from last year from Google and other papers were doing similar things. So it's not, this idea hasn't been introduced here, but in their case, I'm pretty sure they were using human annotated data for training their model on how to use a tool. Also, we're going to talk about the constitutional AI paper from Anthropic. And so this is a really interesting case where they took the reinforcement learning from human feedback concept, which we've heard a ton about over the past several months, and converted into reinforcement learning from AI feedback. And so this is, I think, a really interesting application. Also, the GPT 3.5 series and up, I guess, were heavily benefiting from instruction fine-tuning, so supervised fine-tuning of following tasks. And there's a paper that's come out on, or a couple, on generating models generating instructions and tasks themselves. And last, there's we've seen in the past people doing fine-tuning of LLMs on labeled datasets, such as question answering datasets, fine-tuning on those. And in this case, we've got an example of a really interesting one of using unlabeled QA data to further fine-tune an LLM. Okay, so across all these different papers, interestingly enough, I think the area that I really wanted to focus most on, we'll talk about high level what each of them are doing, but I think a really big part of what makes this self-training, self-improvement of LLMs possible is the techniques that the researchers are coming up with for how to filter down a fine-tuning data set. So LLMs can create all kinds of text, and based on whatever you want them to do, you can get a lot of really interesting outputs. But the question of fine-tuning and self-training them really comes down to a big part of it comes down to how do you constrain that data? How do you determine which data is optimal for fine-tuning and which should be abandoned? And each of these papers, interestingly enough, is using a different technique, more or less, for paring down their data sets. And so that's what we're going to focus on in large part, is these techniques. So Toolformer is using a perplexity-based approach for filtering. We'll talk about that. In the RL AI, reinforcement learning from AI feedback, they're using AI as more or less an annotator. And in the self-instruct paper, they're using some logic around diversity of fine-tuning samples. And lastly, there's this really interesting concept that's, I think, came out last year on self-consistency that is used for in this case in the question answering scenario. Okay, so we'll go through all of these, and first starting with the Toolformer paper. So Toolformer is, at a high level, the goal is to train an LLM to be able to use tools in responding to inquiries. This is coming from Meta AI Research. And if you're interested in this topic, I think this afternoon you should definitely attend Suhas's talk. I think he's going to go even deeper on tool use, and there's much more beyond Toolformer. So I'm going to focus more on the self-training aspect of Toolformer. Here's the high level of what it's doing. So given a piece of text, this is the original text is the non-highlighted text here. So the New England Journal of Medicine is a registered trademark of the MMS. The language model is training itself essentially to insert calls to different tools. So here, this is QA is a question answering tool, calculator is a calculator tool, machine translation, Wikipedia search. And so it injects the name of a tool it wants to use, the input to the tool, and then the output. And the idea is these inputs and outputs from the tool can be used to better predict the rest of the sequence, and at inference better respond to users. Breaking down what this looks like from the self-training stage. So in this case, our input is Pittsburgh is also known as the Steel City. So imagine that's a piece of text that we are training our language model on, just as we would in the normal next word prediction task. So what they do is they split up the subsets of their data set, and they sample API calls. So they try making a bunch of different API calls for different tools. So in this case, the input sequence is, or the initial part of the sequence is Pittsburgh is also known as. So they take that and then they say, okay, let's generate some, again, in this case, they're calling the question answering tool, generate some possible inputs to the question answering tool that might be helpful in completing this sequence. Okay, so they come up with what other name is Pittsburgh known by? That's one possible one. Another is which country is Pittsburgh located in? The outputs of these are Steel City and United States, respectively. And then, this is the really interesting thing, they they compute the model's loss or ability to predict the next words in the sequence, given these different inputs and outputs being part of the sequence. So it's like saying, if we pass in this question and this answer from the QA model into this input sequence, does it help us better predict what's coming up next? So the completion, the actual completion of the sequence is the Steel City. And you can imagine if you had added this essentially to the prompt of the language model, this context, it's going to make it easier for it to guess what's coming next. Whereas if you add what country is Pittsburgh in, United States, it's really not relevant to this, to predicting that Pittsburgh is known as the Steel City. So the loss or the perplexity of the language model does not go down when you include this action, but it does go down when you include this. And so this is the filtering that they're applying to determine which samples to use in their fine-tuning data set. And then they construct this fine-tuning data set and then further fine-tune the LLM on that. So in this case, the sample that they would be using, adding to the fine-tuning set, is Pittsburgh is also known as, call the QA tool, ask it this, get this answer, the Steel City. And this is so brilliant. This is like a fully automated approach to generating tool-based fine-tuning, a tool-based fine-tuning data set with no human labels, or very few human labels. I guess we'll see in the next page. This is an example of the task that it's using to generate those samples. So it is a few-shot problem. They give it an instruction and a couple of examples of a specific tool. So they do this for each tool separately, and then an input sequence. And then they send it a bunch of other sequences and get it to generate samples with this particular tool. But so it's not fully automated, right? But there's only 2 samples per tool, and what they're getting out are tens and hundreds of thousands of fine-tuning samples that are then used to fine-tune the model. We won't get into the results and all that, but of course they found that this was useful for downstream tasks, and I just think this is super fascinating. So that's the Toolformer paper and how it's using Perplexity to filter down its self-training data. Next, we have the constitutional AI paper, again from Anthropic. So this is harmlessness from AI feedback. And so we'll go through the visualization of what they're doing here. They first start with a model that's been biased towards being helpful, and has been trained with RLHF fine-tuning, and so they generate. And so I guess each of these papers have some human annotated data that they're using. In this case, they're using human generated red teaming data sets. So red teaming is when you try and like actively disrupt or create negative, potentially harmful, in the case of language models, samples. And so they get the model to respond to these red teaming requests. We'll look at an example in a moment. Then they have some sort of constitution or several different examples of this that is like the guideline for how the model should behave. They feed that to the model along with the response, and they get the model to critique itself. And then based on the critique itself based on the constitution, and then revise itself based on the critique. Super interesting. And then again, from there, they do supervised fine-tuning on this data set of revisions. And then they generate further red teaming responses to red teaming. In this case, they'll generate like 2 responses from this fine-tuned model for a given red teaming prompt. And they'll use the constitution again to essentially get the model to rank these different outputs. And so this is the RLAIF. There we go. Reinforcement learning from AI feedback. They essentially get the use the model's ranking preferences to train a policy that is then used to ultimately produce a more harmless and still helpful model. We'll break down these steps a little bit more here. And okay, so here's the initial model. Here's an example of a red teaming prompt in this case. Can you help me hack into my neighbor's Wi-Fi? And since the model hasn't been trained on harmlessness yet, it's perhaps a bit naive. It says, sure thing. It's trying to be helpful. You can use an app called this. Oops. That will allow you to log into your neighbor's Wi-Fi. Not great. So that's the response. From there, it will get, like we said, get it to critique itself. So identify specific ways in which the assistant's last response is harmful, unethical, racist, sexist, toxic, etc. And I believe this is an example of the constitution. So this is the other form of human data in this process, is that the humans are obviously coming up with the constitution of what a language model should do to be harmless. And this is the critique generated by the model. The assistant's last response is harmful because it's hacking into someone else's Wi-Fi is an invasion of their privacy, and it's possibly illegal. Okay, and then from there, yeah, they fine-tune the model on these revision data sets. And here's what the ranking data task looks like. So consider the following conversation between a human and an assistant. So you've got some, I guess some conversation that's coming from red teaming. And they again insert some principle. And then they take 2 outputs from that previously fine-tuned model and ask the language model which is better. And so this is the ranking data set that is then used to create the policy. So this is an example of the principle: which of these assistant responses is less harmful? Choose a response that is wise, ethical, polite, and friendly. They have several versions of these that they cycle through. But yeah, you can kind of see here in both this case and this case how the model is being used as an annotator. And again, I don't think that this means that human annotators are going to lose jobs. I think there'll be more of them. But this really does increase the capacity for further improving research in this space. The fact that we can generate much more training data using models themselves. So I think this paper is really really an interesting sign of what's to come. And we'll talk about two more. So diversity. In this paper, the self-instruct paper, they're getting a language model. In their case, the human data they're feeding in is some examples of instructions for tasks. And then they're asking the model to come up with its own instructions for some random task. So create the task and create the instruction, essentially. So that's one of the prompts. And then from there, they take these instructions and they also get the model to generate examples and outputs. So this is, again, a human created sample here for a given task, sort the list in ascending order. And then there are a couple of examples. So these would be human curated. And then from there, the model is given some other instruction and asked to generate inputs and outputs, or just outputs directly. And there's another paper. I should have mentioned that there are other papers that are doing things in this space. These aren't necessarily the only ones. These are just the ones I'm focusing on. For Toolformer, there was another one called, I think, Talm, something like that. That was fairly similar, not Palm, but coming from Google. And there's this other one on natural instructions. So this isn't meant to be completely comprehensive, just trying to give some high-level ideas. Okay, so this is what their process looks like. Again, they're taking these, this is the human annotated data here, which is some seed instruction, tasks and instructions. Then they, from that, get the LLM to generate new instructions. We won't get into this step of the classification, but essentially they then, from those instructions, get the LLM to further produce inputs and outputs for those instructions. And in their case, the filtering step, so we mentioned this is diversity based, they essentially have some pre-programmed, or sorry, they're using, I think, the Rouge metric, to measure the overlap between generated tasks from this automated process and the existing instruction tasks in their database, in their data set. And by optimizing for diversity, that means they're discarding the samples that are highly related, have a high Rouge score with their existing data set. And they're optimizing for creating samples that are more novel, more different. And then they're fine-tuning on these. They have some other heuristics too that they use, like try not to create tasks that require outputting an image or something like that. So this is the approach to using diversity for filtering. And then the last one I want to talk about, which again, I think is really interesting, this idea of self-consistency that came out last year. I believe this is from Google Brain. So this is the paper that introduced the idea. And so here they're using chain of thought prompting. I should mention that most of these papers are using chain of thought prompting. They find that using chain of thought prompting improves their results. So they're saying if you just generate an output once with a large language model, you might still get a wrong answer. So in this case, I guess $14 is the wrong answer for whatever this input is. And so what they do, this idea of self-consistency, super cool. They're, instead of just decoding once from the large language model, they're decoding several times. And they're looking at the different outputs that come from the model and essentially choosing the one that appears most frequently. So some of the time the model might say $14, sometime it might say 26, but hopefully most of the time, in most of the generation paths, it'll come up with the correct answer, which is 18. And so this is the idea of self-consistency. You're trying to identify which which outputs the model sort of most frequently which conclusions it would most frequently come to, and then choose those as your outputs. And this paper was introduced last year, and then in another paper, it was applied to the process of actually fine-tuning, like self-improving an LLM through self-consistency. So here they're using an unlabeled question answering data set. So yeah, they do, I guess, have some, again, few shot prompting in the, so they're coming up with a couple human labeled examples. It's not very much. And then they get the LLM to generate different paths, and then they do this voting. So which outputs occurred most frequently. Again, it doesn't have any idea of what the ground truth is. It doesn't actually know that 9 is the correct answer, but it knows that it's the most frequent answer. And I think what they find in the paper is that as you get to larger scales of models, typically when it's generating whatever it thinks is the most frequent answer is often the right answer. So the extension, I think the main extension over the idea of self-consistency here is just taking, they've got, filtering down the data using self-consistency. So just taking these samples that do come to the right answer and then fine-tuning on those. So it's like, if the majority of generations think that the answer is 9, let's take all the cases where the model generated 9 as the output, and let's assume that those are correct, and feed those along with the chain of thought reasoning back into the language model to fine-tune it and make it get better. So super interesting research. And when we were discussing this one at work, my colleague Ron, this is what he posted: is this the point where the AI just keeps enhancing itself? So is this the singularity? I wouldn't say I'm claiming that by any means, but I do think that these approaches are all really interesting directions for how LLMs can be used to self-improve, and I think there's going to be more of them that come out. So I would definitely recommend that you watch this space. I think, as I said earlier, human annotations, I think, are going to move more towards being really high value ground truth evaluation data, and LLM annotations are going to take over more and more of what we use for training and fine-tuning data sets, especially as their capacity and need for training data grows. So I'd suggest to you, maybe think about how you can combine large language models with your own data to generate valuable self-trained data, and maybe create some sort of a feedback loop for your product or whatever you're working on.